Hello and welcome to Chapter 2, Gravitation and the Motion of the Planets, where we will be talking about the different models for different motions of the planets, whether they were geocentric or Earth-centered, or heliocentric or sun-centered models and scientific theories throughout the years. And at the end of this, we will also come to understanding of gravitation as put forward by Sir Isaac Newton and its role in both developing astronomy and physics as well. In order for an idea to be scientific, it must follow the scientific method, which is to fundamentally make observations or do experiments and use these to test out any theory that you have for the natural world. So if the pre-existing theory explains observations as experiment equally well, choose simplest theory, publish peer-revised review, and propose new or high-precision experiment or observations to extend the theory's realm of validity, and prepare tests of theory in the new realm. And then if it doesn't work out, then if no theory is adequate to explain observation/experiment, modify the existing theory or develop a new theory. Make predictions from new or modified theory and prepare tests on new theory. So both of these are just iterative tests on different theories, and sometimes something will get thrown out, sometimes it won't. But the way that we know that it's scientific is if we do these tests and follow this scientific method. A scientific theory is an explanation of observations or experimental results that can be described quantitatively, that is in terms of equations, and tested formally. This mathematical description used in a scientific theory is considered to be a model of the real system. Often, several competing theories describe the same concepts with the same accuracy. In such cases, scientists choose the simplest one, namely the theory that contains the fewest unproven assumptions. That basic tenet, formally expressed by the philosopher and Franciscan friar William of Ockham, is known as Occam's razor, or parsimony. Indeed, the sun-centered cosmology, as refined by Kepler, which we are about to explore, was appealing because it made the same predictions within a simpler model than the earlier Earth-centered cosmology. Remember Occam's razor. Scientific theories must make predictions, which means that they must be possible to be disproved. For a theory to be considered scientific, it must potentially be possible to disprove it. This was put forward by Einstein not as an original idea or anything, but with the quote that no number of experiments can prove my theory true, a single one can prove it false. A theory of the overall structure and evolution of the universe is called a cosmology, so the prevailing Earth-centered cosmology was called geocentric. Geocentric cosmology, consistent as it is with casual observation of the sky, held sway until the 16th century when Copernicus revolutionized our understanding of the cosmos. The biggest and most obvious problem with the geocentric model was that there was retrograde motion of the planets. So when you looked out at the night sky, everything except for the planets and the moon and the sun and the planet's own moons look like they are just moving slowly and held completely in place, while our Earth rotates about its axis and causes the planets or the galaxies and stars to look like they're rotating. However, planets were called wanderers because they didn't look like they were fixed on the celestial sphere. They rotated around, or they went around and around. But they didn't go in very standard types of orbitals like you would see now. So they didn't go around in circles or in ellipses or in parabolas or any sort of things like that. Instead, they would go across the sky and then double back, which is called retrograde motion. Ptolemy, the last great Greek philosopher, came up with a geocentric explanation of the planet's retrograde motion. The early Greeks, working in what we now know is an incorrect geocentric cosmology, developed many theories to account for the occasional retrograde motion of the planets against the resulting loops of the planets traced out against the background stars. One of the most successful, albeit incorrect, ideas was expounded by the last of the ancient Greek philosopher, Ptolemy, who lived in Alexandria, Egypt. His basic concepts are sketched in figure GD21, which is just the figure on the right. Each planet is assumed to move in a small circle called an epicycle, the center of which moves in a larger circle called a different, whose center is offset from Earth. As viewed from Earth, the epicycle moves eastward along in a different, and both the epicycle and the planet on it revolve in the same direction, counterclockwise in the figure. The ancient Greek astronomer Aristarchus of Samos, circa 310 BCE through 230 BCE, proposed a more straightforward explanation for planetary motion, namely that all the planets, including Earth, revolve around the Sun. The retrograde motion of Mars, for example, in this heliocentric sun-centered cosmology, occurs because the faster-moving Earth overtakes and passes the red planet. The occasional retrograde movement of any planet is merely the result of our changing viewpoint as we orbit the Sun. The ideal that is beautifully simple compared to the geocentric system with all of its complex planetary motions. Unfortunately, this didn't exactly catch on. It was then that the Polish mathematician, lawyer, physician, economist, cleric, and artist Nicholas Copernicus resurrected Aristarchus' theory. Copernicus was motivated by an effort to simplify the celestial scheme, and eventually this heliocentric cosmology did just that. The Copernican revolution got off to a rocky start. Copernicus incorrectly assumed that the orbits of Earth and the other bodies around the Sun are circular. As a result, the positions of his theory predicted were no more accurate than those predicted by the geocentric cosmology. Pursuing the heliocentric cosmology, Copernicus determined by observation which planets are closer to the Sun than Earth and which are farther away. Because Mercury and Venus are always observed fairly near an angle to the Sun, he correctly concluded that their orbits must lie inside of Earth's orbits. The other planets visible to Copernicus, Mars, Jupiter, and Saturn, can sometimes be seen high in the sky in the middle of the night when the Sun is far below the horizon. This placement can only occur if Earth comes between the Sun and a planet. Copernicus therefore concluded also correctly that the orbits of Mars, Jupiter, and Saturn lie outside of Earth's orbit. Today, Mercury and Venus are called interior planets, while all the planets farther from the Sun than Earth are called superior planets. The geometric arrangement among Earth, among other planets, and the Sun is called configurations. For example, when Mercury or Venus is directly between the Earth and Sun, we say the planet is in a configuration called an inferior conjunction. When either of these planets is on the opposite side of the Earth from the Sun, its configuration is called a superior conjunction. Enter Tycho Brahe, one of the richest men of his time. Tycho rejected both Copernicus's heliocentric theory and the Ptolemaic geocentric system. He devised a halfway theory called the Tychonic system. According to Tycho's theory, Earth is stationary with the Sun and the Moon moving around it, while all the other planets move around the Sun. The angle between the Sun and a planet viewed from Earth is called the planet's elongation. A planet's elongation varies from 0 degrees to a maximum value depending on where we see it in its orbit around the Sun. At greatest or eastern or greatest western elongation, Mercury and Venus are as far from the Sun as angle as they can be. The superior planets all have maximum elongation of 180 degrees. When either Mercury or Venus rises before the Sun, the planet is visible in the eastern sky as a bright star and is often called the morning star. Similarly, when either of these two planets sets after the Sun, the planet is visible in the western sky and is then called the evening star. Because these two planets are not always at their greatest elongations, they are often seen very close in angle to the Sun. The positioning is especially true of Mercury often making it hard to see from Earth. At maximum elongation, Venus is nearly halfway up the star at sunrise or sunset, and therefore quite noticeably moving during its own orbit. Because they are so bright and sometimes appear to change color due to the motion of Earth's atmosphere, Venus and Mercury are often mistaken for UFOs. The same motion of the air causes the road in front of your car to shimmer on a hot day. Planets further from the Sun than Earth have different configurations. When one of these planets has the same right ascension as the Sun, i.e. is behind the Sun, that planet is said to be in conjunction. When a planet's right ascension is 12 hours different from the Sun, i.e. when it is on the opposite side of the celestial sphere from the Sun, the planet is in opposition. It is not difficult to determine when a planet happens to be located at one of the key positions. When Mars is in opposition, it appears high and bright in the sky at midnight. Note that at conjunctions, oppositions, or other prominent configurations, the planets and the moon are not necessarily in the plane of the ecliptic. This is because of their planes and orbits are slightly tilted with respect to the ecliptic. That is why at conjunction, planets and the moon are not necessarily directly in front of or behind the Sun. When any three astronomical bodies are in precisely a straight line, such as during a solar or lunar eclipse, or when Mercury and Venus passes directly in front of the Sun as seen from Earth, these bodies are said to be in syzygy. Let us again explore a synodic and a sidereal day, this time for a planet which is inside of Earth's orbit around the Sun, rather than just assuming that it's orbiting around the Earth, as we did with the celestial sphere. So recall from your study on the moon in chapter 1 that a planet's sidereal period is the time it takes that body to make one complete orbit of the Sun as measured with respect to the distant stars. An observer fixed at the Sun's location watching that planet would see it at one point of the celestial sphere go around the sphere and end up at the same place it started from. The sidereal period or orbit is the length of a year for each planet. The other useful time interval that Copernicus uses is the synodic period. The synodic period is the time it elapses between two successive identical configurations as seen from the Earth. The period can be from one opposition to the next, for example, or from one conjunction to the next. The synodic period tells us, among other things, when to expect a planet to be closest to Earth and therefore most easily studied. During Tycho's lifetime, there was an explosion of a new star out in the distance. Now, people didn't want to admit that was a new star or that it could be a new star because they wanted to say that the Earth was perfect and the cosmos were perfect, and that meant that there couldn't be any difference between the cosmos a year ago and the cosmos now. We know this isn't true now, but at the time it was the prevailing ideal. And the way that Brahe or Tycho proved that the object which was seen exploding for 18 months was out in the distance and not close by was using the ideal of parallax. So if you see on the left-hand diagram, when two people look at a tree that is close by from different angles, from different positions, then the tree is going to look like it's at different positions based on how far away it is from each of the observers. And from there you can calculate where the tree is given that information. This is also something that you see when you're looking at your nose. When you close one eye, it will look like your nose is to your right side, and when you close another eye, it looks like it's to your left side. And when you have both eyes together, your vision and your brain doesn't want to deal with that, so it kind of just ignores it. But what Brahe did, or Tycho did, was to look at the exploding star, or the supernova, and find that when you were at two different observatories very far away, because the star is so far away, the angle that each of them makes with respect to the other is in observing the star is basically going to be a parallel angle. So they're basically pointing in the same direction because the star is so far away, and if the star was closer, then they would be pointing at some angle where you would be able to tell where the star was at that given time. So using this, he was able to prove that there are stars living and dying or being born out in the cosmos rather than just having a basic understanding or a basic cosmos that never changes whatsoever. Copernicus was the first scientist in a while to create a heliocentric universe, but unfortunately, it had one big problem, which was that instead of everything being in a circular orbit around the sun as Copernicus assumed, it would turn out that they were in elliptical orbit around the sun. So in order to make the stronger evidence and to find the better fit to the evidence that they had, we have to move on from Copernicus to Kepler. So Kepler's first law, which is 3 laws that he made describing the motion of planets or comets around the sun, is that the orbit of each planet around the sun is an ellipse with the sun at one focus. So if you are unaware, an ellipse is basically just a squashed out circle. It follows a certain mathematical formula which will be useful if we get to describing ellipses mathematically, but for now, all that you have to know is that it's a squashed out circle with the orbital eccentricity designated by the letter E, which ranges from 0, a circular orbit, to just under 1.0, nearly a straight line. So, figure 2AB shows the sequence of ellipses and their associated eccentricity. So the more eccentric an ellipse is, the more squashed it is going to be. And it also is going to explain why we were having those small problems with the circular orbit, where an ellipse is a squashed out circle. It's not quite a circle, but it does approach one if you have an eccentricity of 0. His second law was that a line drawing a planet and the sun sweeps out in equal areas in equal intervals of time. So, for example, on this diagram, you see a planet that is moving around a sun in the elliptical orbit that we were describing in last slide. But as the planet gets pulled towards the sun, it gets faster, because pulling something, as we're going to go into more detail, causes something to get faster. But as it moves away from the planet or from the sun and moves out in its orbit to the farther reaches, it goes slower, because moving away from something that's pulling on you causes you to go slower. So what happens is that these two red lines, or these two red triangle or pie shapes, cause are of equal area, while the one that's farther away is moving slower and the one that's closer is moving faster. But since it's farther away, it turns out that this sweeping is exactly related to the area that's going to be swept up. So how much slower you're going in conjunction with how much farther away you are and able to sweep out a higher area, ends up just completely canceling out so that it's always going to be the same amount of area swept of the ellipse over any given time period, where a time period is 1 week or a month or half a year or anything like that. And then the Kepler's third law is that the square of a planet's sidereal orbit around the sun is directly proportional to the cube of the length of its orbit's semi-major axis, where semi-major axis is defined as the distance from the center of the ellipse to one of its farthest out axis points, so the most squashed out it is, and the semi-minor axis is the distance from the center of the ellipse to its closest point, so how far squashed in it is. And basically, Kepler just found that the square of that sidereal period is equal in Earth years is equal to the semi-major axis in AUs, so the difference between the Earth and the Sun cubed. So if you look at Earth, the average distance between the Earth and the Sun is 1 AU. So that cubed is 1, and p squared is going to be 1. So that means that 1 year is 1 year for an AU of 1. Where again, 1 AU is 1 astronomical unit, is the average distance from the Sun to the Earth. In order to talk about these big units, we have to bring in astronomical units, where 1 AU is 1.5 times 10 to the 8th kilometers, which is somehow about 9.3 times 10 to the 7th meters. And 1 light year is about 9.46 times 10 to the 12th kilometers, which is about 63,200 AU. The second used unit of length is a parsec, where we have light years, which are how far a beam of light travels in 1 year, and a parsec is the distance at which two objects separated by 1 astronomical unit make an angle of 1 arcsec. Imagine walking on a journey through space beyond the orbits of the outer planets, watching the solar systems as you move by. The angle between the Sun and the Earth becomes smaller and smaller. When they are side by side from your perspective, and you measure the angle between them as 1 arcsec, which is 1/3600th of a degree, you have reached a distance that astronomers call 1 parsec, as shown in the figure below or the figure on the next page. The parsec turns out to be longer than a light year. Specifically, 1 parsec is equal to 3.09 times 10 to the 13th kilometers is equal to 3.26 light years. From this diagram, you can see a more clear value explaining how you get a parsec with 1 arcsecond angle between them and 1 AU actual distance between the two. So quickly, I want to just do one of these explanations where it shows how you convert from one unit to another unit. So the nearest star other than the Sun is 4.2 light years away. How many miles away is it and how many kilometers? I don't care. I'm going to ask how many parsecs away is it. So you have the value in light years, and what you want is to get the value in parsecs, knowing that 1 parsec is equal to 3.26 light years. So because 1 parsec is equal to 3.26 light years, if you put 1 parsec over 3.26 light years, then that is just multiplying by 1, which means that you can just put it in any equation that you want to put it. So 4.2 light years times 1 parsec per 3.26 light years the light years cancel out like an algebraic number. So just like an algebraic variable, the parsecs and the 2 light years cancel out because you have 1 light year over another light year. So that gives you 4.2 over 3.26 parsecs, which is equal to 1.3 parsecs. Galileo Galilei from 1564 to 1642 was one of the first of the new wave of scientists, or first of the scientists who actually did start to use the scientific method. So he's not exactly there yet, but he is pretty close. And if I say that Newton invented physics, who we're going to get into in a couple pages, then Newton based physics off of the natural philosophy of Galileo Galilei. So in 1610, Galileo also discovered 4 moons near Jupiter. Today, in honor of their discovery, these are called Galilean moons, or satellites, another term for moons. Galileo concluded that the moons orbit Jupiter because he saw them move in straight lines from one side of the planet to the other. He did not see them move in elliptical orbits because from Earth we see their orbit edge on. Confirming observations were made in 1620. These observations all provide further evidence that Earth is not at the center of the universe. Like Earth in its orbit around the Sun, Jupiter's 4 moons obey Kepler's third law. The square of the moon's orbital period around Jupiter is directly proportional to the cube of its average distance from the planet. Meaning that Galileo was one of the first scientists to really help with Kepler's laws and to be able to make material out of that. And from Galileo we get Newton. Isaac Newton was an English scientist in the 17th century who discovered 3 laws when he was 23 years old and on quarantine from the plague, which basically, I think, introduced physics to the world around us. First law, the law of inertia, is that inertia is a property of matter that keeps an object at rest or moving in a straight line at a constant speed unless acted upon by a net external force. That means that if a object is moving just straight out into space, nothing holding on to it, it will keep moving straight out up into space with no forces acting on it because there are no forces acting on it. There is no natural state for these objects to be in. This is also called no privilege reference frames among certain physicists, and it's not as obvious as it sounds. We tend to think that this is obvious because we live in 500 years of Newton, or we've lived with 400 years of Newton at the very least, and we understand what's happening. But Aristotle stated that all objects would go to their most natural state, and the air would go into the air, fire would burn up and go around in the same way that air does, I suppose. Water would float into the ocean, and then if you placed a rock in a valley, then the rock would fall down, go down the valley, and end up stopping in the middle of the valley because it is closest to the center of the earth, which means that it is closest to its natural state of being. So, what Newton's first law states for us is that there is no natural state of being. No matter what velocity you're going at, the laws of physics are going to be acting the same for you if you're going in a bullet train at 100 miles per hour relative to somebody who's on the platform. Then both of you are going to have different experiences, which we'll get into much later in the course. But the laws of physics do not change between them. as long as you are going at a straight line at a constant speed. However, this means for us and for Newton that in order for the objects to be going around in a circle, or to be following to be following an orbit around the sun or an orbit around the planet, there must be some force that is pulling them towards that object. And then what Newton's second grade discovery was the idea that the force that pulls the apple from the tree is the same as the force that pulls the planet to the sun. And from here, he was able to also develop Newton's second law. The acceleration of an object is is directly proportional to the net force acting on it and is inversely proportional to its mass. So we've been using the term force, and you can probably guess what it is. It's just a push or a pull. But the way we mathematically defined it now is not even saying F equals ma. It's more saying that if you have a constant force, then acceleration is inversely proportional to mass, where acceleration is a, and mass is m, and F is force. So mass is a quantity that all objects have, or not all objects, but all atoms have. So electrons, protons, neutrons are all made of objects with mass. And how much mass something has is related to how much the force of gravity acts on something. But it is also related to how much a force is acting on something, or how hard it is to move something. So how hard it is to move something, its inertial mass, happens to be the same as the gravitational mass, or the mass that causes weight. So something with more mass is going to have more weight, but weight ends up depending on where you are in the universe and how far away you are from an object that's pulling gravitationally, whereas mass is always going to be the constant no matter where you are in the universe. And Newton's law, the law of action and reaction, states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So what this means is that when you push on something, it always pushes back. No matter what forces you're looking at, there's always going to be some net force that is pushing in the opposite direction and is causing you to causing there to be no net forces in the universe, just something pushing against each other and experiencing force from the second object on the first object, as well as from the first object on the second object. So for example, what this means is that when you pull on an object, or when you have the sun pulling on your spaceship, then you are also pulling on the sun with the same force that the sun is pulling on your spaceship. It's just that the mass of the sun is so much bigger than the mass of your spaceship that because acceleration is indirect or is inversely proportional to mass, the acceleration or the change in speed over time. So whereas speed or velocity is the change in distance over time, and is very easy to measure, acceleration is the change in velocity over time, and is the change in distance over time. So that change is going to be much less noticeable for the sun than it is with going to be with your respect to your spaceship. This ultimately leads to conservation laws, or the fact that certain things are conserved and don't change under certain circumstances. So if there's no force that's outside of our system, something we don't account for, then linear momentum is conserved. P, which is linear momentum, is equal to m times v. This has several causes, but the main one is going to be Newton's third law, which states that the amount of force that you can apply over one object for a given amount of time is equal to the same amount of force that you can apply on another object, on the other object in the system for the same amount of time. And what this ends up meaning when you do the math is that linear momentum, or m times velocity, is conserved. So any momentum that is caught up by the second object is lost by the first object, and vice versa. We also have kinetic energy, which is equal to 1/2 mv squared, and is units of joules or Newton meters, where Newton is the unit of force, which is kilogram meters per second squared. So if kinetic energy is changed by work being done on an object with the work equal to the change in kinetic energy. And if you don't want to calculate exactly how much force is being applied over a distance, work equals Fd, then you can create this kind of rule that we have called potential energy, where potential energy is the capability of a force to cause a change in kinetic energy. Total energy, kinetic energy plus potential energy, is conserved in any interaction as long as you account for all the forces in the system. So as long as there is no net work being done from outside of the system, then the potential energy and the kinetic energy is going to be constant. And then the potential energy is given by G m times m, the masses of the two objects which are pulling each other, over the distance between the two objects, r, when you're talking about gravitational potential energy using Newton's calculations to find how those forces work in space. But if you're relatively close to the surface of the Earth, then this becomes m times g times h, where g is the acceleration due to gravity of an object that is dropped near the surface of the Earth, which is going to be a constant for any type of object that is dropped. That's one of the things that ends up happening. And this is going to be somewhat linear, which makes it useful when we're talking about potential energy close to the surface of the Earth, because potential energy is just height. When you look at any sort of potential energy versus distance or versus x or anything like that graph, you can just assume that potential energy is going to work like an object rolling down a hill, because potential energy close to the surface of the Earth is just dependent on height, or how far up you are in the y-axis. Then that means that it is basically just a graph of the potential energy when you look at a graph of how high up something is in the y-axis height versus x in this case, which we're going to call the distance along the ground. So at the top of the roller coaster, you have zero kinetic energy and zero potential energy. But as you go down, you gain potential, you have zero kinetic energy and 100% potential energy. But as you go down, you lose potential energy, which is converted into kinetic energy and are 50-50. When you get at the very smallest part of the ride, you have zero potential energy, but the maximum amount of kinetic energy, because all of your potential energy has been converted into kinetic energy using the idea of conservation of energy. Then you go back up and you have about 75% of the kinetic energy, but only 25% of the potential energy. This is fun, but as we said earlier, the Earth is both spinning and revolving. So it is both rotating and revolving around an object. So we were talking about linear motion and linear momentum, which is conserved when there's no linear force acting on it. But there is a force acting on it. There's the force due to gravity acting from the sun as the Earth moves around its in its circle. And basically what that does is it changes, as we said, when talking about Newton's or Kepler's second law, it changes the speed or the linear momentum you have because you're moving farther and closer to the sun, and it is giving you momentum or is taking away momentum. This is why it is useful to introduce the concept of torque, which is the rotational equivalent of force. So as long as there is no torque, where torque equals R cross F, or R times F times the sine of the angle between them. So if you're using a wrench, the maximum force torque that you're going to get in order to rotate a bolt is going to be R times F, with the force and the wrench arm being perpendicular to each other. That's what the sine of the angle means. What this ends up meaning, though, is that if there's no torque that is applied, there can be a force that's applied, then something called angular momentum is conserved, where angular momentum is equal to R cross P is equal to R mv sine of the angle. So as R gets bigger, mv has to get smaller if there's no torque. And the way that we know there's no torque is because the force of gravity goes directly in the line pointing between the two objects. So because it goes directly along the line pointing between the two objects, there's no angle between the rotational arm and the F. That means that there is no torque, which means that angular momentum is conserved. And as you can see, or as you have probably seen if you've watched the Olympics or anything like that, when you have your arms out and have them, that is going to increase what's called your moment of inertia I, which is going to make it so that you spin slower than if you have your arms in, which decreases your moment of inertia I and increases the velocity that you're spinning. So this ends up being equal to R cross P, or R times sine of the angle between them, or I, the moment of inertia, times the angular speed, which is something like a record player plays at 33 and a third revolutions per, or your so it's basically just the revolutions per minute unit. We use radians per second instead for our SI units, but it is just a measurement of how fast something is spinning around its axis. Earth waltzes with the moon around the barycenter and cannot follow a smooth elliptical path around the sun. Kepler's first law dictates should occur. In fact, both Earth and the moon follow oscillating paths, and the lower mass moon moving quickly toward and away from the sun more than does the massive Earth. It is the barycenter of the Earth-Moon system that follows the smooth elliptical order. The same discussion applies to all the other planets with Moon, keeping this in mind when we speak of moons orbiting their planets in chapters to come. Newton also discovered that some objects orbiting the Sun can follow non-elliptical path. His equations led him to conclude that orbits can also be parabolas or hyperbolas. In both cases, each body would only make one pass close to the Sun and then travel out of the solar system, never to return. To date, all but one of the objects observed in the solar system were formed here, and their initial orbits were elliptical. Some of these objects, namely some comets, small bodies of rock and ice, and some asteroids and meteoroids, both the latter being small bodies of rock and metal, have had their orbits changed by collisions and close interactions with other bodies orbiting the solar system. As a result, these deflected objects gain enough energy to develop parabolic or hyperbolic orbits and therefore leave the solar system forever. Then one piece of space debris known to have entered our solar system from interstellar space was a piece of rock and ice, a comet that has been named Oumuamua, Hawaiian for Scout. It is on a hyperbolic orbit, having passed closest to the Sun on September 9th, 2017, is now leaving the solar system never to return.